So in this video I'm going to show you how our buffer tree works. Initially we have a buffer tree node class which stores a leaf boolean which tells us if this node is a leaf or not, a keys list, a child's list, and a buffer list. The buffer tree class stores the root node, the t, which is basically the minimum degree of each node in the tree. So in accordance with the properties of the buffer tree, the maximum degree of each node will automatically be t into 4, and the nodes with buffer dictionary stores each node that has a non-empty buffer at the current time. If you scroll down, so how it works is that initially we've given the buffer tree a t of 2, so it means that the minimum degree of each node will be 2 and the maximum degree will automatically be 4 into 2, which is 8. We have a few functions. The buffer insert function, what this does is it inserts the element and the operation ID into the buffer at the root node. When the buffer at the root node gets full, it is pushed down into its child nodes and divided evenly. So after that, the buffer at the root node is empty again. Then we can insert more values into the buffer at the root node. It keeps doing this till all the buffers in the tree are full. When all the buffers in the tree are full, the buffers at the second last level are emptied and the buffers at the level above them are pushed down, so the buffer at the root node is empty again and we can insert more operations into it. The operation ID is I, D, and S, which stands for insert, delete, and search respectively. So as you can see here, I'm going to insert this list into the buffer tree with a key of I, which means insert each element. And I'm going to print the tree so we all can see it. As we can see here, the tree is printed. The level shows the level of the node. This shows how many keys are present at the node, and this shows the individual keys. Now we have called this empty all buffers function because in the end, to get our resultant tree correctly, we have to empty all the buffers so that all the operations are carried out. If we do not empty all the buffers, we can see we do not get the proper tree. The in-order traversal basically gives us an in-order traversal of the tree, so we get all the keys in increasing order, as you can see here.
Hello, this is Nasir. I'm going to show you an implementation for orthogonal line segment intersection, which is performed using line sweeping. The idea is to find all the intersection points between the lines that are being rendered onto the screen. We start with a vertical line on the left side of the screen, which gradually moves across. We maintain a list of all the line segments and we check which line segment is being currently cut by the vertical line. We add that segment to our buffer tree. Then we check intersections between elements of the buffer tree. If a line segment is no longer being cut by the vertical line, then we remove it from the buffer tree. To visualize the process, we are using Turtle in Python. Let me run it for you. So right now we can see lines being randomly drawn onto the screen. We chose vertical and horizontal lines because we wanted it to be neat and tidy. You can see that intersection points start to pop up from left to right, and this is going to continue till over here, but this takes a lot of time. The code is not efficient because currently we are not using buffer trees because it hasn't been fully implemented. We are using a list to store all the active segments. We hope to perform a timing analysis of the different number of lines for list and buffer tree to show that the buffer tree really does improve the efficiency of our algorithm. Thank you.